The finite element method is a way that engineers invented to solve equations like structural equations. What are the stresses on a bridge? If a big truck drives across a bridge, what are the stresses? If a tall building is in wind, in a storm, what are the stresses on that structure? Will it stand? Constantly, and on a ship. So Lloyd's Insurance would take the design of an oil tanker and would ask whether that ship is safe under storms at sea. So it's, for mathematics, it's solving differential equations. Differential equations describe nature. And these are complicated equations, not linear equations. Materials are stressed, and the problem is to compute that stress. The history of the finite element method actually begins in Russia with Galerkin, who created a method to take the differential equation, which is a continuous problem. A computer can only solve a finite problem, a discrete problem. So our goal is to take this continuous differential equation, the stresses on the ship as it goes across the ocean. One way is to take derivatives and replace by finite differences. So the derivative, the slope of a function, in calculus is about the slope at a point. The finite differences give you the slope between one point and the next point. So that's one approach, a very important approach to making the differential equation discrete, finite, solvable by a computer. The Galerkin idea is a different one. Different starting point. Galerkin took some trial functions that he hoped whose combinations could be close to the right answer. And the problem then is to find how much of each function goes into the good answer. We're talking about approximations, not exact solutions. But engineering is involved with approximations all the time. If we get one decimal place, 2 or 3 decimal places, error of 10 to the minus 3 would be quite okay. So Galerkin's idea was choose some functions whose combinations would be close to the right answer. 100 years later, because of the computer, it was possible to work with 100,000 functions. Galerkin worked with 2 or 3 functions, 2 or 3 trial functions. So he had to make a very close guess of the solution. But if we have 100,000 functions, they can be just maybe little hat functions, just up and down again. Simple functions. And their combinations, if we have many, can give us close to the correct answer. So the whole idea of the finite element method is a way that it's a combination of Galerkin's idea of test functions with the idea of simple functions, where the physics is simple, the equations stay simple, but you have many functions. And that's what a computer is happy with. So that instead of the differential equation, we have a big system. Remember, our unknowns are how much of each hat function goes into the solution. It's the coefficient we want, the number that multiplies each of the hat functions when we add them together. So we get a big system of equations for those numbers to multiply the hat functions. And the system is very well organized for mathematics. So the questions like, how close is the approximation? If I approximate a function like e to the x by 1,000 hat functions and take a combination of the 1,000 hat functions to be close to e to the x, how close will it be? If I take 2,000, how much closer do I get? So those are the questions that that applied mathematicians, numerical mathematicians are expert at studying. So I'm really now explaining the part of mathematics in the big picture. If I give go back to the history again. So Gilbert had the idea of trial functions. Then the idea of choosing simple functions. That came in, from Courant, who was a mathematician from Germany, came to New York. The same idea appeared in Beijing. I went to meet Feng Kong, who had the idea and had no computer in China to use the idea. And the idea also appeared in Europe and in Russia. It was an idea of the right time. Engineers have done the important work of creating the big system. So now it's if a finite element code has thousands and thousands of lines, companies specialize in preparing a code to solve physics problems, engineering problems, and you pay for their work in preparing the software, preparing the code. And mathematicians, their part has been, still is, to understand what is going on, how to solve those many equations, how close is the solution to the original problem. It's a teamwork. Actually, I would say the finite element method is the greatest example in engineering of the teamwork of thousands of engineers and mathematicians. All big structural engineering companies need finite elements, or the automobile industry, the airplane industry, and thousands of engineers have contributed to the code, contributed new trial functions, and mathematicians have contributed something to the understanding of the accuracy. Nothing's ever perfect. All numerical methods are waiting to be improved. Finite elements came first for structural problems, and that's a class of equations where nothing is going to move too far. The bridge just moves a little bit, and it's important to know how much. But think of the difference between that and fluid problems. So in fluid problems, a river is flowing. A jet engine is sending jet out. It's creating shock waves. Much harder problems. The frontier, the difficult problems are really those where there's a velocity involved, where there is fast movement. And for that, we need new finite elements that are adapted to fast movement, to the appearance of shock waves. So you could say for solid mechanics, we're good. For fluid mechanics, we have much work to do. For gas mechanics, we have much work to do. So, I want to make clear that the whole history of finite elements and the present day of finite element theory is a success. It's a very positive experience. It was my first occasion to talk to engineers, to understand what problems they wanted to solve and what mathematics could contribute. So right now I would say that the fluid problems and the gas problems are back in the hands of the engineers to try new ideas, new functions, see what is successful. And then in this case, maybe mathematicians come maybe a little later. Also wavelets, people think, why don't we use wavelets as trial functions? So that would be coming out of mathematics and other directions. It's a success story.